Okay. Good morning. My name is Kai He. I would like to welcome everyone to the Warren Distinguished Lecture. And today it's my great pleasure to introduce today's speaker, Dr. Ilenia Battiato, to kick off this year's seminars series. Dr. Battiato is an associate professor in the energy science and engineering from Stanford University. She earned her master degree in environmental science in polylateral Milano in 2005, followed by a master degree in engineering physics and PhD in engineering science, computational science from UC San Diego in 2010. And before she joined Stanford University, she held a faculty position in Clemson University and San Diego State University, and also was a postdoc fellow at the Max Planck Institute in Germany. So Ilenia's research focused on advancing the fundamental understanding and computational modeling of complex multi-physics and multiscale systems, especially related to critical energy application like CO2 sequestration, electrochemical process. So her work has been widely recognized. So she is currently serves as the vice chair for the Golden Research Conference in the flow and transport in the permeable media. And also she is a recipient for the DOE Young Investigator Award for her innovative contribution on the multi-scale modeling, which I believe is related to today's work. So without further ado, so please join me to welcome Ilenia for her talk.
Thank you. Thank you for the introduction. That was very kind. So first of all, my name is Ilenia Battiato. Thank you all for being here. Thank you very much for the invitation. It's really an honor for me to visit University of Minnesota and also Minnesota for the first time. I've never been here before. And I look forward to interactions with you all, although probably they will be short because I will be leaving today, but it wasn't as cold as I thought, and I've been doing just fine. It's beautiful, so yeah, thank you again for having me. As you probably can guess from the title, today I'm going to talk about some of the work that we have done more recently, I would say starting around 2020, so during the pandemic, on upscaling in automation, and in particular what we believe to be a technique or an approach that can really push the boundaries of multi-scale model development, which is specifically the integration between symbolic deduction and numerical computing. However, before I get to that point, I actually want to share with you a little bit of the journey that led us to start working on this project, that actually it's a pursuit that has been kind of 10 plus years in the making. So you'll see some of the origins of where all this then came about and what were the questions that led to where we are right now. So as I started thinking about, where this all started and what really drove our interest in this, I found this quote to be actually quite representative of the way that we as a group think about modeling. And so this is a quote from Karl Popper. You might know he was a contemporary philosopher, wrote extensively on a number of topics, including philosophy of science. And in one of these writings, he wrote, "If we are uncritical, we shall always find what we want. We shall look for and find confirmations, and we shall look away from and not see whatever might be dangerous to our pet theories. In this way, it is only too easy to obtain what appears to be overwhelming evidence in favor of a theory, which, if approached critically, would have been refuted. In order to make the method of selection by elimination work and to ensure that only the fittest theories survive, their struggle for life must be made severe for them. That sounds quite apocalyptic, but what really we're going to talk about and what has driven really most of my research was trying to understand when continuum theories that we really used a lot actually fail or are not reliable anymore, but that's really to advance our ability to use them better and maybe to develop models that can improve when those theories may not be accurate anymore. And so where do we think about all these big questions? So I work on multiscale and multiphysics processes. And the reason why we are focused on these systems is for three primary reasons. The first one is that these systems are ubiquitous in a number of applications. It is not by chance that I included very, very different applications that we are actually interested in. Here you might recognize this is a geologic porous medium. This is a rock seen. This is a microfluidic chip that we fabricated and we embedded a rock in it. Other porous structures that you can find in battery electrodes, and even in, you find porous media that as part of the heat shield of a thermal protection system that is used to protect capsules as they re-entry from space through the atmosphere. And so the heat shield is a porous material which is imbibed in a resin, and it has to have specific properties such that can essentially absorb the thermal shock to protect the payload that is inside the capsule. So they're ubiquitous, so we can find them anywhere, and I'm sure you have in mind a porous structure that you think is very important. But ultimately, the other two reasons why we are looking into them is because this type of multiphysics and multiscale processes or systems really put enormous strains both on computational resources and theoretical modeling. They're just hard to handle. Okay, and so what do I mean by multiphysics? A multiphysics systems is a system that is characterized by a number of different physics that occur at the same time concurrently and can be coupled in various different ways, right? So we can have advection, diffusion, reaction, heat transfer, electromigration, all kinds of different physics. A system is multiscale if all these different types of physics actually take place in complex heterogeneous environment that exhibit a hierarchy of spatial scales. And so one such example is porous media. We know that porous media, regardless of the application, exhibit an heterogeneity of length scales, from the pore structure that, compose the matrix to the system scale device, whether it is, again, a geologic porous media or a battery pack or whatever you might think of. Oftentimes, things can get even more complicated than that in the sense that physicochemical phenomena on one scale or a fine scale can really affect and can be strongly coupled to the performance or the behavior of the system at a much larger scale. Now, in this talk, so this situation adds further complexity, and I'm not gonna, investigate what we do when this happens, although you can do certain things, but we're gonna touch marginally on it. But there are some ways that this can be handled. Of course, that's not the end of it, because in general, on top of all the physics, we can also have incredibly complex reaction networks, okay? Reaction of all kinds. Now, in this case, I just picked from the internet, like a reaction network that is relevant to hydraulic fracturing, but again, in any application, CO2 sequestration, hydrogen storage, electrochemical system, inside reaction in batteries, you can have in very large reaction networks. So then the question is, what do we do, right? When we want to model this type of systems, what options do we have? And so we have at least a couple of options, like basic options. The first one is to use, let's say, pore scale models, fine scale models. Now, I'm going to focus my attention specifically on reactive transport. So we are going to be thinking about porous media that are fully saturated with one phase, so not multi-phase at the moment, so one phase, and then they carry solids that can interact in the liquid phase or between the liquid and the solid, okay? Can undergo heterogeneous reactions. And so if we want to model advection, reaction, and diffusion in this type of systems, again, we can use pore-scale models. If we look at the hydrodynamics and we have low Reynolds number, then of course we can use Stokes equations to describe the velocity and pressure distribution at the pore scale. And for the transport, we can look at an advection diffusion equation where these would represent boundary conditions that you have on the solid-liquid interface if you have an heterogeneous reaction. Let's say your solute reacts with the grain, right? Then you would have something like this. The flux is prescribed, can be nonlinear, and all kinds of things. So that's one option. The other option is to use continuum scale models. So there are many fundamental differences. The first being the fact that at this scale, we do not distinguish between the solid and the liquid anymore, but we treat the entire system as an effective continuum. And then we attach to our new domain, which would be, let's say, this continuum domain, some effective parameters. Now, the first thing to notice is that if we want to model exactly the same physics at a different scale, the equations that we're going to use are going to be different, and they can be significantly different. So, for example, in this case, we would use Darcy's law to model momentum transport, and for mass transport, we would use an advection reaction dispersion equation. Now, these equations are not written anymore for pore scale quantities, so for the pore scale concentration or velocity, but they're written for average quantities, which are indicated with the brackets, and these are averages over relevant representative elementary volumes, okay? The other characteristic is that, again, the form of the equation can change. As you can see here, we have a reaction term that was, oh, I'm already outside of the, so we have a reaction term that, so what was before a boundary condition at the pore scale now becomes actually a source term in the continuum scale equation. And the other feature is that we have effective parameters that we didn't have in the pore scale model. So we have permeability, we have a dispersion tensor, we have porosity. Okay, so now what are the advantages and drawbacks of each approach? Well, so for the pore scale, the good thing is that they are obtained from first principles. So from a theoretical point of view, they are the most robust, right? So we are confident in their predictions, and we know that they will predict correctly if we are able to solve those PDEs in the proper domain. However, the main complication is that in order to be able to solve things at the pore scale, we need to know the pore geometry everywhere in the structure. And again, because the system is multi-scale, that's generally not the case. This is even more so if you think about geologic media, where in fact the structure is completely uncertain. Right? But even if we knew the structure, maybe you are thinking about engineering application where you actually design the material. So you know exactly how it is done. However, you still face, because of the multi-scale nature, significant computational costs, which generally is actually prohibitive to run full-scale simulations at the full scale. On the other hand, continuum scale models do not require the pore scale geometry. They just require a knowledge of the effective parameter, the distribution of effective parameters on this continuum. Because of that, we can solve, numerically much larger computational domain with a limited computational cost. But the problem is that they are approximate. Right? So they are built on certain approximations, so they rely on simplifications and assumptions, and the validity of these approximations need to be ascertained before these models are deployed. If we don't do that, then we lose predictivity, or we don't know whether the model is going to perform when we expect it to be. So what we are interested in our group is really trying to avoid the situation where we get surprised. We don't like surprises, right? So then the question is, how do we choose or build a model? And so then the idea is really everything should be made as simple as possible, but not simpler, in the sense that you would like to be able to model accurately the physics you are interested in. So you shouldn't simplify more than allowed. And so this was really the original pursuit, right? So what we wanted, the first question that we asked a long time ago was really, can we actually build predictive models of multiscale systems where we actually a priori know what the error will be? Can we really do this? But then that became a much larger question, and we wondered, like, can we actually integrate the physics-based model development of multiscale systems with actually what we call physics-based model deployment? Ultimately, what we wanted to do was to use the mathematical theory to, excuse me, to build all the models at every relevant scales rigorously, but at the same time, after we have a menu of different models, then we would like to be able to deploy them, in real-world applications in a way that is optimal. So where we have control on computation, but we also have control on accuracy. And the connection between these two branches is what we call diagnosis criteria or applicability conditions. So those diagnosis criteria essentially define under what conditions that model that you have derived can be actually applied and preserve the accuracy prescribed by the theory, okay? So that was the challenge that we were pursuing. And so in order to do this, the first thing that we needed to do a number of things. So first of all, going back to the original question, can we build models with controlled accuracy? The second was we want to include realistic complexity. We want to be able to handle realistic complexity. And third, we want to be able to do this computationally efficiently. And all of it, we would like to do it fast, and we would like to do it general, right? We would like to be able to create a framework that then can be applied in different application areas with different physics and so on and so forth. So let's start with controlled accuracy. So again, the question was, can this model, can continuum, well, first of all, continuum scale models, will they fail? And if so, when and why? Okay? And so before going into the details, I just wanted to put out there the general philosophy of what this coarse graining or upscaling effectively does, because it's ultimately not that complicated, although it can be a little intricate sometimes. So the general idea of coarse graining and so traversing scales is something as follows. So let's assume that you have a function, u, and this could be, your physical property. Density, velocity, temperature, concentration, doesn't matter. This is defined on a porous scale domain and satisfies a certain partial differential equation. So essentially, there is a conservation principle that this quantity satisfies. And because I'm not attaching to a specific physics, I want to represent it very generally. So this is some kind of differential operator that acts on this quantity, right? And this is equal to some source term. Now, the general objective of any upscaling methods that exist is the following. You want to obtain a partial differential equation for the spatially averaged quantity of interest in this kind of form. So you want to write a differential operator that now acts on the average quantity, let's say average density, equal to this, the average source term. Now, the important aspect here to remember, as I mentioned before, is that these two operators may not be the same. These may be different, although oftentimes we assume that they are the same, okay? But they may be different. Now, and this is how you define an average. Essentially, that average quantity is just some, integral of our porous scale quantity over a representative elementary volume. Now, what we used in chart, so that's the general philosophy of what any upscaling method does. Now I'm going to do a crash course in homogenization theory in one slide, okay? So we use specifically as a method homogenization theory. So the way this works is that you start from a real porous medium that you conceptualize as being a periodic structure composed by repeating unit cells over here, whose size is epsilon, and epsilon is much smaller than 1. 1 now can be thought of as the dimensionless size of your macroscopic domain, so of this entire macroscopic domain. So you start from your pore-scale system of equations, so this is the physics that you know to be right, and then you apply this homogenization theory that is all hidden behind this arrow. So you apply homogenization theory, and after these derivations, you obtain a continuum scale equation that has the features that we discussed before. It's written for the average quantity, it has effective parameters, and so on and so forth. So this is the continuum scale equations, you get that. Then you get the effective parameters in the continuum scale equations. The other element to know about this theory is that these effective parameters can be calculated through what's called a closure variable. Now, what is a closure variable? A closure variable, which is this chi over here, is just a variable that satisfies another boundary value problem that you solve just locally at the pore scale. So essentially, how does the entire workflow looks like? You do your derivation, you get the continuum scale equations, you get the effective parameters, and you derive this. Then if you were to solve it numerically, the way you would do it is that you start from this, you solve this boundary value problem in the repeating unit cell, you calculate the closure variable, you plug the closure variable into your effective coefficients, you calculate the effective coefficients, you plug them into your continuum scale equations, and you have a full consistent model. Okay, so that's it. That's all there is to it. Okay, so there are some details, but that make it complicated, but that's okay. So what are the advantages of this approach? Well, of course, if you can get to that equation, this reduces significantly computational costs, and the theory also provides you known error of these approximations of that equation if you apply that equation within the proper regimes, okay? So you know all this. You know when that model will be predictive, and you know the error. The disadvantage is that essentially everything that I did not show you behind this red arrow, which is the mathematical derivations. These derivations can be incredibly time-consuming, and they are intricate, error-prone, and they are analytically intractable for complex systems. Okay, but at the time, when we were asking the question of whether continuum scale models even broke down, we didn't care about complexity because we lived in the world where we did math by hand, right? And that's a nice place to be because complexity becomes the tuning parameter. So what we did was to try to answer our question for a system that was simple enough that we could handle analytically by hand. And when you do that, then you are in a modeler's dream, right? You have your spherical cow approximation, and it's all beautiful and nice, and there is something similar in porous media where you have a spherical grain approximation, but this is just to say that you can construct your reality in a way that you can handle it, okay? But this is not to dismiss how much you can learn from the spherical cow approximation, which I'm going to demonstrate just in this very simple example. So this is flow in a channel. You know that flow in a channel can be considered as a canonical porous medium, okay? Let's assume that we have steady flow, so we just have our parabolic velocity profile. We are not going to care about the flow, we are just going to care about the transport. And so we have a contaminant or a reactant that is being transported, advected, and diffuses inside that channel. And the dynamics at the pore scale can be represented by this advection diffusion equation. The additional element, though, is that we assume that this solute can react with the walls of the channel. Very innocent reaction. This is a linear reaction, nothing that should perturb us, right? So if we want to build the continuum scale model of this pore scale equation, the first thing we need to do is to define an average. And in this case, for this geometry, the most obvious average is just the average across the vertical cross-section. If you apply this averaging operator to this partial differential equation and you do a lot of math, that's not my paper, but somebody else's paper, they derived this equation, okay? They derived this equation with these effective coefficients over here. And so everything looks perfect, right? So we have what we expect. We have an advection, reaction, dispersion equation. It's a 1D in space because we have integrated over the y direction, so we have deleted that dependence. We have the effective reaction rate, fine. That depends on, of course, the pore scale one. That has to be like a relationship, and the geometry. And then there was this dependence on Damn-Collar number. Now, this Damn-Collar number, excuse me, this Damn-Collar number is a dimensionless number that represents a ratio of timescales between the diffusion timescale and the reaction timescale. So if Damn-Collar number is very small, it means that the diffusion timescale is very short, so diffusion is very fast, okay? And the opposite is true. So when I first saw this model, I didn't see anything until I saw something that was quite disturbing. So I said, okay, let's assume now that I'm not changing the physics, but I'm just making my wall more and more reactive. Again, I live in my imaginary world, so I can do that. And so what I thought was that, what if I just increase this K, right? I increase K, I increase Damn-Collar, fine. I increase Damn-Collar, but when Damn-Collar becomes greater than 3, the sign changes. Which of course is highly problematic, because if the sign changes, it means that the macroscopic behavior is changing too. I'm changing something that was maybe an absorbing boundary into a desorbing boundary, but I'm not changing anything at the pore scale. The physics is exactly the same, so what's the problem? And so then it's when I started thinking, well, the problem is that this model is not always true, which is fine, right? That doesn't take anything away from the model. We just need to know that before we start using it. And in fact, the applicability condition of this model is that the Damn-Collar number be less than 3. Okay, now of course the same argument we then started investigating, and we tried to do it for more complex systems. Again, still very simple compared to the realistic reactions that people have to handle, but this is again the hardest thing we could handle by hand, which was an A plus B in liquid phase goes to C, and then C reacts with the solid and transforms into S, right? So this is again all fictitious. You have different Damn-Collar numbers because you have different reaction rates. We also have a Peclet number, which is another dimensionless number. And we wanted to upscale this system. So the pore scale equations are just a system of coupled advection, diffusion, reaction equations for concentration of A, concentration of B, and concentration of C. And then we have appropriate boundary conditions at the interfaces between the liquid and the grains, right? So because it's only C that it's reacting with the solid, then that's the only flux that is non-zero, okay? And we had some kind of non-linearity because we wanted to see how things turned when we had nonlinear behavior. So you do the procedure, you upscale, you do the math, ultimately you get a system of equations exactly as you would expect. These are advection, reaction. I know that the notation might seem a little intimidating, but essentially this is what you would write. It's like an advection, reaction, dispersion equation for C, where you have this solid liquid reaction, you have an extra term, and then you have the effective coefficients, right, that we discussed before, and we know that the effective coefficients now can be calculated only after solving a closure problem for chi. Now, that's where the interesting part is, right? So how do I find chi? So the procedure tells you that chi needs to satisfy a boundary value problem, that it's something is this, but the caveat is that the only way this local boundary value problem does not depend on continuum scale quantities is only if you have certain constraints on the order of magnitude of Damkohler and Peclet. Saying it backward, what this means is that if Damkohler and Peclet are not in the proper range, then you cannot decouple scales. Okay? Everything is fully coupled. You cannot write a continuum scale equation. Okay? So those are what we call the applicability conditions. So these are the bounds that need to be satisfied by the dynamics for the scales to be separable. So it's not just enough that you have separation of length scales, so that these grains are very small compared to the size of your domain. You also need to have constraints on the dynamics. So this phase diagram is essentially what allows us to identify the applicability conditions. If the combination of your dimensionless numbers falls within that colorful region, then you have sufficient conditions to homogenize. And you know that your continuum scale model will represent pore scale processes within the accuracy that is prescribed. But if you're outside, you don't know anymore. So these are only sufficient conditions, not necessary. And so the important thing that we discovered at the time is that now we have constraints on the physics. But what do they mean? Why do we have constraints on the physics? Well, essentially, it's actually very intuitive. These conditions, what they do is simply to enforce that your gradients of concentrations at this fine scale are kind of flat, are kind of smooth, right? And why that needs to be? Because imagine you have a sharp gradient of concentration. So concentration changes really a lot within your pore space. But what this homogenization or any upscaling does is essentially saying, no, look, you don't need to resolve this. You can just replace it with an average value. But you can imagine that the sharper the gradient is, the poorer this approximation is going to be, okay? And it becomes poor to the point that you cannot guarantee anymore the error that you wanted from the theory. And so you can verify all this numerically, right? So the way you would do it is that you run your pore scale simulation, you run your continuum scale simulation, and then, of course, you can plot, one on top of the other, but really what we only look at is not how close or far those curves are, but only if the absolute error between the averaged pore scale solution and the continuum scale solution is within the error bounds prescribed by the theory. So what we look at is only this error plot that we're going to see. So if the error is below epsilon, then the model is verified, okay? So now, what we had learned by then, and I need to go fast, so we had learned a few things. So homogenization theory, and in fact, by extension, any other upscaling method, could and should be used not only to derive continuum scale models, which is as they have been historically used. They actually tell us much more than that. You can determine also the applicability conditions of the models that you have derived so that you know when you can use them safely. Actually, it allows you to determine rigorously and self-consistently whether this macroscopic model has the accuracy and predictivity that you want, because through that error analysis. And on top of that, but I'm not going to be able to cover this, you can rigorously derive actually coupling conditions for multiscale formulations within the upscaling errors. That's another topic, but you can do that. And so all this was beautiful, right? It was perfect. Everything worked. Everything fell into place. We, now understood the potential of discourse graining theories. They could do a lot of different things. In particular, they also allowed you to construct multiscale models that seamlessly connected adjacent scales without parametrization. If you knew certain information at the pore scale, you knew exactly how to calculate the parameters in the continuum scale equation, which is like the closure problem. And so we said, well, this is wonderful. Let's go to complex systems. Well, then, at the moment we did that, it was a disaster. It was a disaster because Again, the arrow, the red arrow, well, that is awful. So the mathematical derivations that are required to actually calculate that, they are painful, to say the least, okay? They are tedious, time-consuming, prone to error, long, it's a lot. If you want to calculate the applicability conditions, that even requires more time. And the problem is that complexity is not a tuning parameter in realistic systems, so we were, gloriously stuck. And it is bad. So this is how bad it is, and that's not the end of it. That's not all of it either. Okay, it's bad. And so then we said, okay, how do we come out of this? And we understood that there was actually, we started again, we stepped back and we said, wait a second, we recognized that there was actually a bigger picture maybe that we should have been thinking about. Ultimately, all this, developing multiscale models, is a branch of computational physics. And we know that computational physics sits on these three pillars, right? The discipline, what I call disciplinary modeling, is essentially experiments, right? Experimental techniques that are specific to that specific physics. Then you have the numerics, and then you have the applied math. And we had done in the past decades incredible advancements in these two areas. We can now see and probe scales that we could never probe before. We essentially have, reached the maximum scaling performance in numerical computing, but practically we still did math like we did 200 years ago, most of it, honestly. So then we said, okay, then we need to automate. We need to move things forward in that third pillar. And so the idea, really the framework did not change, but what we wanted to do was to automate this entire thing. And so I'm gonna go fast. So we went and looked into symbolic computing. I'm sure everybody has heard of it, but essentially symbolic computation is just the science and technology that aims at automating a wide range of processes. This is not new. It's actually routinely used in certain branches of applied math and theoretical mathematics, for example, combinatorics. It's always used. It's also used in certain branches, maybe a little bit more narrow in computer science. However, it's never used in the context of applied math for computational physics. It's like the automation of formalisms or theories that are, for example, that we use in multiscale modeling that was never done. And in fact, not only this thing is not new, I mean, it's really old. So the first idea, the first proposal of symbolic computation actually came from a woman. So, yeah, women. Ada Augusta Countlets of Lovelace, 1842, and she wrote this beautiful excerpt on commenting the Babbage analytical engine, which is considered the first computer, right? So she wrote, many persons who are not conversant with mathematical studies imagine that because the business of the Babbage analytical engine is to give its results in numerical notation, the nature of its processes must consequently be arithmetical and numerical rather than algebraical and analytical. This is an error. The engine can arrange and combine its numerical quantities exactly as if they were letters or any other general symbols. And in fact, it might bring out its results in algebraic notation where provisions made accordingly. And so that's what we did, right? So essentially what we did, we automated the procedure of homogenization so that everything was allocated to computational resources, right? So we developed the software Symbolica that is written in Mathematica and automates the upscaling procedure by multiple scale expansion. And now, because we don't have to do any math, we are essentially not constrained by complexity, okay? And so what does Symbolica do? So what Symbolica does is to take in sets of 4-scale or 5-scale equations, right, as complex as you want, and then returns the upscaled system of equations, the closure problems, and the definitions of the effective parameters. And again, because all that arrow is now allocated to computational resources, the speed up is massive. So we go from the speed up estimated, it's 10 to the 5, generally to do I will admit that Symbolica redid my PhD thesis in 10 minutes. So that was an humbling experience, but it's true. Okay, so yeah, some cases we started with those. So now it has a certain structure. I'm not going to go through this, but there is a way. So then after building Symbolica, what we did was to essentially test it, right? And so again, we tested on my PhD thing. That's how I know that it did it in 10 minutes. So that's the case that we had before, that I had done again 10 years prior, by hand. And essentially what Symbolica did, it upscaled the system of equations for 625 permutation of dimensionless numbers. So every dimensionless number needs to be assigned an order. And so depending on how many dimensionless number is, you have different permutation of values. So it upscaled essentially 625 times, right? And it found 72 possible upscalable configurations, so where you can separate scales, and it did this in 8.5 minutes. And it rebuilt the phase diagram that we had derived analytically, with the exception that it discovered that actually the phase diagram that I had calculated was too restrictive. So I had been overly conservative in my identification of the applicability conditions, and Symbolica found that in fact you can upscale in more places than I thought you would be able to. Because I did it once and tried to generalize it, and instead Symbolica did it 625 times. Okay? So, of course, you do the validation, and I'm not going to go into that. The idea is that whatever model Symbolica produces, you will test it numerically with that same procedure. Porous scale, you average it, continuum scale, compare the errors, evaluate if they are under the error bounds, okay? So it's all validated. Again, all that matters is that all these curves are below this threshold. And then we, of course, wanted to try a case that we would have never done otherwise, which is like, again, a synthetic case, 10 species. And this is impossible to do by hand. By the way, Symbolica would upscale two cases, one that is more reactive, one that is more advective, in 65 seconds. Again, what we care about is these error plots, and the equations that Symbolica produces are in fact correct. Now, these are just the numbers. Again, this is effectively what I told you before, that was I should write my PhD thesis, and that's like 10 minutes. Now, because of I have limited time, but I just want to say that the fact that this is not just about doing things faster, okay? The technology actually enables discovery, because now, since we are not constrained by our own limitations, we can actually create a generalized part of the theory that otherwise would be very difficult to generalize. And we did that essentially by generalizing closure forms. So we could essentially derive models in reactive regimes that before we could not coarse grain, okay? Now, why is this interesting? Because, again, I'm going to just point you to the equations up there, because if you start pushing the derivations where it's still legal, but now you can do it because the machine is doing it, you actually start obtaining emergent terms. So you start discovering terms that you, or me, or anybody, well, I don't know anybody, but I definitely wouldn't have never put in that equation. One thing that is interesting, for example, and again, there is way more to this, but is that this is just a very trivial reaction. C1 goes into C2, can decompose back. And so you would expect like a very standard advection, reaction, dispersion equation. But in reality, what you see appearing are these cross-coupling terms. They almost, so you see that you have the standard advection term, which is, the gradient of concentration C1, but now you have this cross-coupling term with the gradient of concentration C2. Okay, so you start having this strange physics that we wouldn't have added in there. Now, how do you know it's correct? Well, we know it's correct because we numerically test it, right? And if we remove those terms, the model does not validate anymore. So the terms have to be there. So is the framework transferable? Yes, we did it for thermal runaway in battery packs, completely different application. I believe I will have to skip that, but I just want to point out that essentially, again, this is just to say that your imagination is the sky, right? So that's a battery pack. You can, again, it's a multi-scale system, right? It has battery cells embedded in a packing material. There are a lot of batteries, 444 per pack, 7,000 per module, 7,000 per pack. Modeling this at this scale, very expensive. You can build continuum scale models. We were interested in thermal runaway. And again, you feed this conduction equation to Symbolica, and you do get, very interesting looking PD. So you start from a standard conduction equation, and you get an advective equation. By the way, the advective term that you get actually represents the propagation of a thermal front as a battery pack blows up. So it can capture emergent dynamics, if the math is done properly. You can do validation. I'm going to skip this because I want to get to the last part, computational efficiency. Now, so we had all this infrastructure, right? And we said, okay, this Symbolica produces stuff, but we always have to test it, which means we have to code it. But now, because these PDEs are complex, they are just ugly. They are long, can be pages long. I mean, and I'm not trying to exaggerate. I really mean it. That's not all of it. This is a piece of an output of Symbolica, right? So then, now to test this, you have to code it in. We actually have done it, but the student who did it was not happy. Rightly so. So the student had to take that equation, had then to calculate by hand the weak formulation of it, so that then he could code it into a finite element solver. I mean, I should buy him something. But so you might probably be able to see all the green check marks, right? Right. But you might not be able to see a red cross over here. There was an error. Of course, how can you blame him? I mean, that's already an amazing job, right? And so that's when we said, okay, you know what? We don't even want to do that anymore. We're done. And so we say now, because the outputs are so complex, really, now the numerical implementation and the validation becomes problematic in itself, but we need to test these models. We might have coded something incorrectly in Symbolica. We need to be able to catch it. And so that's when we said, okay, then we are going to do symbolic-numeric integration. So now we have the Symbolica part that does the upscaling thing, and then there is another code that essentially takes the Symbolica equations and then transforms them into code, okay? So what does Numerica does? Well, takes, again, the output of Symbolica and then automatically calculates the weak formulation, does the automated time discretization, language transformation, then feeds it into a FEM solver. We, of course, wanted to try on a case that we would have otherwise have never done. This is like, again, a synthetic case, 7 solids, 7 precipitates, 9 different solid boundaries. You do the upscaling, you have 31 closure variables. It's just a nightmare, complete nightmare. And so this is just the numerical solution of the closure problems. And these are again, what we care about are the concentration plots, right? The errors, they're all below this red line for all the species. Symbolica, this one took some time. Actually, I wonder why that long. I'm still curious about it. And Numerica took 4 minutes to create the code once it had Symbolica's output. So with this, we have some current capabilities. Again, I briefly mentioned we can do also heat transfer with heterogeneous inclusion. We actually have coded in the ability to handle the coarse graining of vectorial equations, because ultimately we would like to do multi-phase flow. maybe, and other things. But so what are the concluding remarks? So, my claim here is that automated symbolic deductive engine can enable scientific discovery because they can eliminate the human bias in the way we, know things and learn things, right? Symbolic numeric softwares can accelerate the rigorous and quantitative understanding of complex systems. And again, as I mentioned before, this allows us to reduce human bias in our understanding of complex systems because oftentimes we may not have, again, our intuition is built on experience, right, as physicists. But now when, complex systems, they can span, portions of the parameter space that we may have never experienced before. So we may not have the proper physical intuition to predict what goes in there. And so I think that as we start going towards more complexity, then I think that these tools might be really helpful. Now, if you're interested in generalization, again, you can put here your favorite multiscale physics. We are also technically interested in generalizing different mathematical procedures. Again, all of this is based on one algorithm that is agnostic of the specific math. And these are some publications related to Symbolica, and these are the acknowledgements. So Kyle is the main developer of Symbolica. He's now Lawrence Fellow at Lawrence Livermore National Lab. Ke is the person who developed Numerica. So thanks to him too. And Brandon is the one who developed the capabilities to do vectorial equations. With this, I run out of time. Oh no, I don't have a thank you slide. Well, thank you for this. I don't
Thank you. Thanks a lot for the excellent and engaging presentation and a lot of inspirational scientific figures. Okay, so we have time for a couple of questions.
The place where your presentation breakdowns for me is a unit cell. Okay. Can Symbolica deal with stochastic differential operators? And if the answer is no, when will the stochastic differential operator version be available?
Oh, then we need to talk. Let's write a proposal together. Yeah, no, we can. We are working just with, with deterministic PDs. But, there is stochastic upscaling that shares, a lot of features, right? And of course, I would love to demonstrate that this can be applied to a number of different things. And I would love to do that, but we are kind of limited. But yeah, I agree with you. That would be very cool. Yeah, but no, I can't do it now. Sorry.
So what happens when the operator is nonlinear and you can't write the closure?
Well, so homogenization theory is based on, perturbation, right? So you do need to linearize, right? And so then the point is that, so you can try to generalize the closure to kind of truncate, later and later and get a better approximation, but you need to have a way to formulate a closure, right? So these methods are all based on perturbation theory. So the way they handle nonlinearities is by, linearizing it, and then you can add more terms, which now we can potentially do because we don't have to ourselves to keep track of all these the terms. We can truncate at any order. But yeah, that's an intrinsic limitation, I think, of the method.
So the multiphysics stops at high Reynolds numbers. You can't really handle that.
Yeah, I would. Yes, and high Reynolds number. Yes.
Hi, thank you for your presentation. So I have a side question. It's about the computational cost. Did you use a supercomputer to solve those numerical equations, or just a regular?
No, this is all like desktops. We are not using supercomputer because for us, so we are not doing really, I would argue, like high-level numerical implementation where we want this to be. For us, it's more like, okay, we stop at the proof of concept, and once the error are, below, then, then we pass it on to the numerical people, right? We don't do a lot of, high-level optimization of the software to enhance performance. So this is all desktop kind of things. Yeah.
Thank you.
So it should be faster, for sure. I think there are questions on it.
Okay, Judy.
Very intriguing talk and fascinating methods. I just have one question about the reactive transport in this single pore, because I know without reaction, people have developed analytical solution for like shear-induced dispersion coefficient. So I wonder, are there any analytical solution that can take into account the time? Yeah.
Not that I'm aware of for high reactive, for when things break down. I don't think that there are. But again, I don't know. That was, I haven't looked back into it for. I'm not aware of that specific case, but it might be. Yeah, I don't know.
Thanks.
Yeah, probably as a numerical guy, I'm interested in the robustness of the algorithms, Symbolic-Numeric, especially related to whether you will observe any error during the duration, and also is about the uniqueness. Whether, because we know when we use the Mathematica to divide the equation, sometimes they have different way to generate the right.
Yeah. So, although it is claimed that Mathematica could do this, that's not true precisely for that reason. Mathematica allows you sometimes to perform operations that are illegal, and you won't know until you substitute a number in your variables. For this reason, we used a foundational basic algorithm that is very robust, but essentially does not use any of the embedded function in Mathematica. Essentially, just use the data structure of Mathematica that represents equations as trees, as logic trees, and then our algorithm essentially has a way to traverse the tree and check for dependencies consistently so that you don't incur in those errors that sometimes Mathematica function incur into. Yeah, so we don't use Mathematica functions. We just use Mathematica as a host.
Okay.
You know what I mean?
Yeah. So that does it mean the Symbolic-Numeric, the output is deterministic?
Yes. The output
Okay.
is-
Okay. Thank you. Any other question? All right. So please join me to welcome again.